Well, greetings. Thank you everybody for tuning in to today's ASBI monthly webinar. Hopefully you're here today to hear David Birrcher talk about guidelines for design and construction of segmental bridges for rail. I'm Greg Freeby, the Executive Director of the American Segmental Bridge Institute. I have just a few introductory remarks to make and some announcements to make before we turn over for David's presentation. If you're not following me already on LinkedIn, I encourage you to do so. Follow me as well as the American Segmental Bridge Institute. You'll find out about events coming up like future webinars. Of course, you can always find that information on our website, but sometimes social media can be a better platform to get those little announcements. Some additional announcements I have this morning is to talk about the July webinar. That's coming up the last Wednesday in July from noon to 1 Central. It's called Insights on Concrete Segmental Bridge Construction Practices. And Mr. Wade Bonzon from FIG, who is the chair of our Construction Practices Committee at ASBI, will be leading that webinar and sharing some of his knowledge and expertise about segmental bridge construction. The topic of today's webinar is somewhat tied to this new publication that ASBI just published back in March, Guidelines for Design and Construction of Segmental Bridges for Rail. I'd encourage you to seek out that publication, particularly after today's presentation, that David is going to be talking a lot about segmental bridges for rail. Another event we have coming up for folks on the West Coast, actually for folks all over the U.S., is our Construction Practices Seminar, which is August 15th through 16th in Seattle, Washington. This is a really good seminar that goes into much more depth and detail about segmental bridge construction beyond what you might find in some of our webinars or even in our Construction Practices Handbook. And initially, a lot of people looked at this and said, well, it's really only for contractors. And the reality is, this is a great seminar for anybody involved or anybody who wants to be involved in segmental bridge projects. It really goes into a lot of depth and detail. Registration for this is already open on the ASBI website, so I'd encourage you to go over there to sign up. The day after the seminar then in Seattle, we'll be hosting another in-person session of our grouting certification training. We did a training back in April in Austin. We believed that was going to be the only one we were going to offer in person this year, but there's been enough interest in the Seattle area to have a session in Seattle. So again, this event is available on the ASBI website for registration. And finally, the other event we have coming up this year is our convention and committee meetings. It's October 31st through November 2nd at the Hyatt Regency in Austin, Texas. We have a really good technical program pulled together, some really enriching activities, not only from a technical learning standpoint, but also some really great networking opportunities. So some quick instructions on how to use the webinar today. If you lose your connection, you can rejoin. Just use the link that you were provided, and you will miss content while you are away. We will issue certificates for attendance today, but only to those who meet the minimum time required in the session. And I would ask you to allow at least a week for your attendance certificate to be issued. These aren't auto-generated by the system. We actually go in and verify time and attendance to make sure people met the minimum requirements, since we are issuing certificates through RCEP. And access to the recording from today's presentation, as well as a PDF of the slides, will also be available on the ASBI website at the place where you were likely registered, which is under the Events tab. So at the conclusion today, then we will do some Q&A for pretty much as long as folks want to hang around. If we get to the top of the next hour and you need to leave, you're certainly welcome to do that. That won't impact your ability to get a certificate for attendance. But we do want to try to cover as many of the questions as possible. So then that begs the question, how do I ask questions? And the answer is, well, in your GoToWebinar interface, you should have a little questions click box, and you can click on that and type in your question in the box. We have a moderator who's going to be collecting up those questions as the session goes, and then we'll do a little moderated Q&A at the end. So don't feel like you have to wait until the end of the session. If something comes to mind during the presentation, just go ahead and pop that into the questions box. If you're working on a mobile device, you should have a little question mark in the upper right-hand corner. You can click that, and again, a little dialogue will come up for you to be able to type in questions. And again, this is we are in compliance with the Registered Continuing Education Program, and that is where we will issue your certificates for completion. And again, those are only issued to folks who actually attend the live webinar. We can't issue certificates through RCEP for viewing a video. So with that, I'll go ahead and introduce today's speaker. Our speaker is Mr. David Birrcher. He's a senior bridge engineer at Sistra International Bridge Technologies Incorporated in San Diego. He has over 13 years experience in bridge design and construction engineering. He received his Master's of Science and PhD in Structural Engineering at the University of Texas at Austin and his Bachelor of Science in Civil Engineering at Tulane. His recent complex design build projects include an elevated segmental guideway for the Chicago Transit Authority, the so-called Red Purple Modernization Project, and the third Panama Canal crossing, a concrete cable-stayed bridge in Colon, Panama. David was very instrumental in helping lead the group in the creation of our guide document on rail. And so with that, I'm going to flip over and let David present.
Okay, thanks, Greg. Hopefully my screen is showing up for everybody now, and let's get started. So yeah, happy to be here to talk to you guys about guidelines for design and construction of segmental bridges for rail.
Hey, David.
Yeah.
You might lean into your microphone a little closer. You're a little soft.
All right, I'll try to do that. Does it sound a little better now?
Yeah, that's better. Thank you.
Sure thing. Okay. So Greg mentioned this, but I'll just plug it again. Go on to ASBI's website, download the document. It's the right price, free, so no excuses there. Also like to take a minute just to acknowledge other people that were involved with the working group. Everybody volunteered their time and were instrumental in getting this done, so they deserve to be acknowledged. And then now we'll just briefly go over the outline of the presentation. So a couple slides on introduction, a little bit about design criteria. The meat of the presentation will be on design issues. That's my background, so apologize in advance if that's not your thing. But we will talk a bit about construction and a few maintenance aspects as well. Okay, so introduction. Everything you know about segmental highway bridges applies to segmental rail bridges. So, you know, no knowledge lost there. But there are a few things that make segmental rail bridges unique. And so that's essentially the purpose of the guidelines and what we're going to be talking about today in the presentation. What are those things? You know, and be a little scattershot in that there's, you know, a bunch of different issues that'll all kind of come at you. But we'll try to hit them up one at a time, and hopefully you'll get a feel for what makes segmental rail bridges unique. So this is just a clip from the guidelines. I think Greg had the same quote up there, but again, just emphasizes that we are trying to highlight a few important things that make segmental rail bridges unique. So first thing we'll talk about is design criteria. So you know, one thing you'll learn when you start working on rail bridges, there's not a single technical specification for rail bridges like there is for AASHTO LRFD for highway. There's a lot of great references out there. A few of them are shown here on the screen. A lot of good information, but there's not one that kind of ties everything all together like AASHTO LRFD does for highways. So what does that mean? Well, typically, you know, you still want to rely on AASHTO LRFD, you know, for the fact that it's up to date, and it's constantly being, you know, state of the art. But things need to be added to it. So there's this plus here that needs to be added to accommodate special considerations for rail, whether it's loads, load combinations, different performance criteria. So that typically takes place with a project-specific design criteria. There are a handful of examples from previous projects, other owner agencies in the guidelines in the chapter 3. I have them kind of highlighted there on the screen. And a handful of kind of important considerations when going through and preparing one of these project design criteria. Can't emphasize enough, you know, the need to do a good job here. You got to be thorough, you got to be clear, you got to be comprehensive, and there's really no wasted time in the preparation of these documents, because it'll directly affect how well the project goes. So, you know, we want quantifiable criteria, so numbers, clear order of precedence, some idea of how the guideway and the station, different requirements for those different structures. You know, what are we designing each of those structures to? Which codes? How are they interfaced? That sort of thing. So can't emphasize enough the importance of a good design criteria. Let's talk a little bit now about some design topics. So span type. Segmental rail bridges are often simply supported structures in a 100 to 120, 130 foot range are very common. These relatively short distances between the expansion joints are good for both rail structure interaction and for limiting deflections and vibrations. They're also easy to construct, and so that makes them an attractive choice. One issue that sometimes comes up with these you know, short, simple spans is for rail bridges, you'll have some special track work, whether they're crossovers or switches. And oftentimes the special track work doesn't work well when it's adjacent to a movement joint, a structural expansion joint that has some movement. So to get around this, we use link slab details. These details have been around for a long time, both in rail bridges and in highway bridges, you know, oftentimes to reduce the number of expansion joints you might have. And so effectively what they do is replace the plinths with a big concrete kind of continuous slab across the joint that the track work can attach to. Of course, sometimes you have to have a long span structure or a multi-span unit, and that is obviously possible. And it just, a little attention needs to be played to, you know, these different performance criteria that we'll talk about in a bit in the rail structure interaction. Okay, next we'll talk a little bit about station integration. This obviously is specific to rail structures. So typically classify how the guideway and the station interact by 3 different options. So option 1 is the platform directly supported by the girder. That's pretty self-explanatory, kind of showing in the pictures here. Option 2 is a more of an indirect connection. Often this happens with like a shared foundation. So the picture on the left is under construction, but you can kind of see there's a central, you know, dual box guideway kind of going right through the middle through these kind of integral hammerhead vents. And then on either side of the hammerhead vents, you can see these concrete blocks that are eventually going to support station platforms on each side of that central guideway. So this is an outside platform configuration. It's pretty easy on the guideway here because the guideway can just kind of run straight through, and the platform is on either side. And then there's also a center platform configuration shown in the rendering there on the right. Here the box is split, so there's single track boxes on either side now of the center platform, but this also, you know, is sharing the foundation with the station, and has been successfully implemented on several projects as well. I'd say the last category is independent structures. So you may have a really large station structure like you see in the picture on the left, where the guideway kind of coming in there on the right of the picture just effectively stops at the interface with the station. Or you may have something like it's shown in the graphic on the right, where you have kind of independent guideways and a station structure that don't interact really at all. Okay, so how do we sum up? Well, The issue of a center or an outside platform is typically outside of our control, the bridge engineers, that is. You know, operational considerations will likely determine that. But what you would still want to have is clear design criteria, as we mentioned before. Whose responsibility is it? Who's designing, or what code are we using for what? You know, that's always a sticky topic. And then it's all about coordination at that point. You know, coordination is one of those things where you'll hear me say it a few times, I think, today. It's easy to say and it's hard to do. And so it can be even harder if design schedules do not match up. And so what does that mean? Well, oftentimes for precast segmental, the design schedule for the segments gets accelerated because they want to start casting segments ahead of time. And so what ends up happening is you may need to coordinate with a certain discipline, but you're at 100% design, whereas they might only be at 30. And so it makes the coordination job even harder to get what you need out of that coordination. So getting these design schedules compatible is a real important thing. Next, we'll talk a little bit about cross sections. So common cross sections for rail segmental bridges are box girders, which you know, here in the U.S. we're very familiar with, and then U sections, U shapes or channel sections, kind of shown in the graphic there on the right. Those are much more common in other parts of the world, in Europe and other places. So we'll spend a little time talking about those here. Okay, so they have a couple different configurations. There's a wide U, which is kind of analogous to the dual track box girder that you see here on the screen. That wide U will support 2 different tracks. And you know, quickly when you look at it, you can tell, okay, well, visually there's a little less depth associated with the U, and it also can accommodate more vertical clearance. So that's a couple of things right off the bat that the U can provide that the box girder cannot. Fabricated and erected in the same way as a dual track box. So, you know, individual segments like you see here in the picture, cast in a precast yard and erected in a similar way to a dual track box girder. The advantage of the U is that integral parapet. So, you know, the wall there of the U is obviously part of the structural section, but it also can serve a couple other purposes. It can support the evacuation footpath, and can also act as a derailment protection. So you get you know, kind of 3 birds there with 1 stone. There's also a narrow U configuration. So this is more analogous to the single track box girder, and it is you know, its advantage is it can be cast in single spans, you know, entire spans, and then erected as an entire span. So this can be a very fast, quick way of erecting your bridge. So you can see here that they have parallel U's here, so you got essentially a track in each direction, and this is, like I said, a common system being used in other parts of the world. You know, one limitation of the narrow U is that when you've got curves, you've got to then chord the entire spans. So it limits the radii that this system can accommodate, or you know, and or it'll limit your span lengths. So that's a consideration that you have to this type of structure. So to sum up on the cross-section thing, so box girders, as we know, are very structurally efficient, and they're generally more so than the U sections and can accommodate longer spans. Box girders also have that future PT capability that we're familiar with here in the US that the U girders just do not have. But the U sections, you know, like we said, have shallower depth and can give you some better vertical clearance. And then they also have that built-in parapet that addresses a couple other issues that you need to address. And then lastly, the narrow U and its ability to be installed quickly is an advantage. Last thing, I wrote aesthetics down here. I purposely didn't really talk about that because it obviously varies person to person, but that could also play a role in your decision of which cross-section to go with. Okay, next we'll talk a little bit about loads. So obviously we've got loads to deal with here. They are generally agency-specific rail car loads that you'll get for a specific type of car and vehicle that'll be traveling on the bridge that you're working on. That's common. In that more recent AASHTO guide spec document that kind of flashed on the screen earlier, they have introduced kind of a notional live load model that's a little more analogous to the truck and lane load that we do for highway bridges. That's shown there in the graphic below. But anyway, a similar concept to what you're going to get, or to what you're doing for highway bridges. And then also there's longitudinal loads to deal with. So we've got braking on highway, and we have to deal with that here. There's also acceleration that'll be considered, and effectively you just need to apply that according to your design criteria and consistent kind of with the operational characteristics of the train. Typically it can be additive, so you can have braking in one track and acceleration in another if you have like a dual track structure, so don't forget about that. There are transverse loads too. So centrifugal force and curves, just like highway bridges, no surprise there. But this other transverse load is unique to rail bridges. So the picture down in the bottom left is illustrating the load referred to as hunting. So effectively it's a transverse load that gets transferred from the vehicle to the rail on the inside of the gauge. And it's basically as that car might shimmy back and forth trying to find its equilibrium. There's a lateral load on the rail. And so this happens regardless of curves and needs to be applied throughout. Derailment. This is a big one that is obviously specific to rail structures. It can be both vertical and lateral, and generally has a large impact factor associated with it. So it should be considered, early stages in the design, preliminary design, at bid time, because it can oftentimes control some transverse designs of your box. There are anti-derailment curves that can be used that'll help maybe limit the locations that you have to consider. So keep that in mind as well. Okay, next we'll talk a little bit about rail structure interaction. So what is that? Well, rails are typically continuously welded rail. That's the most common type nowadays. And it is exactly like what it sounds. It's rail that's been welded together and is continuous across structural expansion joints of your bridge. And so you can imagine when that bridge wants to move and expand at those joints, rail is going to restrain it in some extent, or there's going to be some interaction, I should say, between the structure and the rail. That interaction is controlled a lot by these fasteners. So specifically in the longitudinal direction, there's a nonlinear relationship basically between the connection of the fastener and the rail, and it has to do with that little steel spring clip that you see there. It's basically linear up to a certain point, and then when it reaches a certain load, it'll slip. So we've got kind of a complicated interaction that we have to address. So we do that with a rail structure interaction analysis. So it's a nonlinear analysis where these connection points between the rail and the box are modeled explicitly. And there's typically three things we want to get out of that analysis. So the first is we want to make sure we don't overstress the rail. So in that design criteria we talked about, there should be really clear load cases or loads that you have to consider for this effect. I should point out that the design of the rail itself is the responsibility of the track designer. But typically what they'll do is they'll give you a certain percentage of the capacity of the rail, a certain allowable stress that us bridge designers can work with, because effectively the track designer doesn't know anything about the configuration of the bridge, the distance between expansion joints, the movement of the structure, that sort of thing. So for these particular loads, we'll apply those to our RSI analysis. We'll get a delta stress in the rail from those loads, and we'll compare that to the allowable to make sure that we're not overstressing the rail for the stress that's allocated to us. The second thing that you might typically be looking for in an RSI analysis is investigating rail break. So what this means is there's going to be a different load case now where we're trying to maximize the tension in the rail, and this will also include temperature effects from the rail itself. So we're going to maximize the tension in the rail, and then as part of this analysis, we're going to analytically kind of create a break in the rail and see where the force in that rail redistributes. So the screenshots that I'm showing here on the screen, the figure on the left shows forces in the rails, before rail break, and then the figure on the right shows the forces in the rails after the rail break. And so, we want to basically look at how that force is redistributing through the structure, make sure there's no issues with that redistribution. But then also, that tension in the rail has to basically go somewhere. It's being transferred to the box, to the other rail components through those slip fasteners that we talked about. And what that does is that creates a gap in the rail. And that distance, the measure of that gap is something that we want to control. There's going to be an allowable limit in the criteria that you have to satisfy. And that's intended to mitigate against derailment if one of these rail breaks were to occur. So that's, let's say, the second category of things that you'll be looking at in your RSI analysis. And then the last thing, and this is kind of touched on a little bit in the previous slide, but the restraint that the rail provides, it's going to generate forces in the structure. And so these forces need to be combined with all your other forces from all your other load cases that you're looking at. And those components need to be designed accordingly. So, there's going to be radial forces if you've got curved rail. And then in the kind of unlikely event that you might have, let's say, a large anchorage force because the rail is terminated on your structure, which is not advised. You do not want to do that. But if you can't get away from it, that there's going to be a large anchorage force at that termination point, and that's going to go into your structure, and your structure needs to be designed accordingly for that. So, again, third category here is what is all this restraint doing to my structure, and making sure the structure is designed for it. Okay, so that's the RSI stuff. Let's talk about another kind of sophisticated analysis, the vehicle structure interaction. So what is this and what is it for? So, because our rail cars are traveling, repetitively over our bridges at kind of, predetermined, loading frequencies, we want to make sure those loading frequencies don't line up with the natural frequencies of the bridge. So that's typically handled a few different ways. There's hard limits on deflection that effectively just making sure that the structure has got a certain stiffness. And then they also typically require that the minimum frequency for that first mode of vertical vibration for the natural frequency there, the structure is at least a minimum value. So 2.5 hertz is a typical number. And then, they may also require a specific analysis, or perhaps if you don't meet one of those limits, you have to do the analysis. But essentially, they may require a vehicle structure interaction analysis, or sometimes it's called a rolling stock analysis. So what is that? So that is a time history analysis where, again, we're looking specifically at the dynamic response of the structure. So again, the vehicles traveling at different speeds will have different loading frequencies, and if those loading frequencies kind of line up or match up with the natural frequencies of the structure, we're going to get some dynamic amplification. So you can measure all this in the analysis and compare that amplification to the impact factor that you're considering in your design, and then you obviously want it to be less than that impact factor to move forward. So that's one thing that you'll do. Another thing that you'll do from the analysis is you can look at the acceleration of the structure itself due to these different loading frequencies, and compare it to an allowable value that is meant to safeguard against rider comfort. So those are two things that typically come out of this analysis. Next here, we'll talk a little bit about seismic. I'll say that seismic is generally similar to the approach that you would do for a highway bridge. There'll be a maximum considered earthquake that you want to avoid collapse to. And then there'll be an operational basis earthquake. So that'll be a smaller earthquake that you want to remain essentially elastic under. Talking about that RSI analysis that we left a few slides ago, there often will be a stress there on the rails that you'll have to meet under this operational earthquake. So you have to incorporate some earthquake loads in that RSI analysis. Next, we'll talk a little bit about some deflection limits. So, highway bridges have deflection limits as well, but there's a few more constraints, I would say, or a few more criteria to meet for rail bridges. We've got a vertical live load deflection. Okay, that's not surprising. But then there's these couple of rotation limits that typically occur or are typically required there at expansion joints. And that's meant to both safeguard the rail and safeguard the operation of the vehicle. So both of these limits need to be satisfied. A couple other deflection related criteria that typically show up. So, we talked about stations previously. If you've got an independent station structure, independent from your guideway, you'll want to check, and there should be something in the criteria about this, to check differential deflection. When someone's getting off a rail car and stepping onto the platform, you don't want them tripping or falling off or anything like this, right? So there needs to be a limit of that. And then kind of the last deflection limit that shows up has to do with creep. So when the bridge is erected, plinths are cast, rails are installed, they're going to be at their theoretical alignment, within the tolerances set forth for that. But over time, concrete segmental bridges, any post-tensioned or pre-tensioned bridge for that matter, is going to creep. Typically, rail bridges will creep upwards because the PT will overcome the dead load. And so over time, you'll get a little bit of vertical movement there of the rail, as shown kind of in that picture on the bottom. Now, that's an exaggerated movement. These are fractions of an inch we're talking about, but it's a good idea to have that criteria laid out so it can be discussed, talked about, and make sure everyone's on the same page and isn't a surprise to anyone later in the game. Okay, and then the last kind of design related topic I've got is systems integration. This is a bit of a catch-all slide. Some of these things might not be classified as systems, but basically what it's meant to convey here is there's a lot of stuff on a rail bridge, more so than on a highway bridge. And so those things need to be coordinated and accounted for, and we'll talk a little bit about that. These slides. So similar with the station stuff, coordination is everything, and it basically amounts to education. You're going to be trying to educate other disciplines on what a segmental bridge is, what the constraints are, what things are important, what things aren't, and similarly, they're going to do the same to you for all their stuff. Again, compatible design schedules make this coordination possible. Without that, it makes it really difficult. So these are some kind of considerations to think about. On the slide here, we're kind of showing just a generic example here of what some of these issues might be. We've got to support these cables along the length of the guideway, and then there might be a spot where we need a big hole in the structure to dive these cables down underneath the structure. Let's see. Okay, another example is kind of shown here on the slide. So again, there may be some posts, some structural posts to accommodate some equipment. There's probably going to be sleeves associated with that equipment. There might be. And then one interesting thing about this one is that presence of that equipment causes the rails to actually get further apart, which in this case required a strut to make that wing work. So this is the kind of example of a kind of thing where, all right, if we need to put in a bolt, embed some anchors, if we need to put in some sleeves, these aren't huge deals. We need to know about them, but not huge deals. If it's requiring us to widen the deck or to add a strut or something like that, these are a bigger deal. So you want to obviously educate these different disciplines on what's important and what's not, so you can identify those things as soon as possible. Stray current, won't get into the science on this. I'm not really qualified to explain it, but effectively what it amounts to is rebar in the plinths and rebar in your deck generally are all tied together or welded together so that any stray current that does leach into the structure can get collected through this continuous bit of rebar and then collected with a longitudinal collector cable, a copper cable that runs the length of the bridge and links segment to segment and links span to span, and then eventually it'll drop down to the ground somewhere. Let's see, other considerations. So the rolling stock itself, has requirements. A certain width is needed tangent track, but then the greater width is needed when there's a curved track. So don't forget about this when laying out and planning the widths of your girders. Track work. Track work, can get complicated, as you can see on the picture there below. Again, sometimes the requirements don't affect the structure too much. Maybe it's just some complicated plinth shapes that the track work designer will give you. But sometimes you have to bump the structure out. It has to be wider to accommodate certain equipment, sleeves, that sort of thing. So again, just want to coordinate and figure out what's important and what needs to be included. Picture on the right is a friction buffer stop. It's only needed when the rail terminates. It doesn't happen often on elevated structures, but if it does, there's typically some large loads associated with that. So those need to be accounted for. Okay, that does it for the design section. Let's talk a little bit about construction. So geometry control is essential for any segmental bridge, but probably more so for rail bridges. The tolerances are a little tighter. The rail alignment will one of the track alignments will control the geometry of the box. So that's how that's handled. Okay, this slide is going to show a video kind of animation that just kind of illustrates how a curved guideway gets cast and how that curve is accommodated in the casting yard. So the screen on the left there is kind of showing the bridge, obviously in its final kind of configuration, and you can see there's a pretty tight radius there. And then the picture on the right is going to illustrate, how segments are cast to accommodate that curve. So effectively, what happens? That segment in blue is the match cast segment, and that segment gets rotated effectively to accommodate and create pie-shaped segments that are needed. So again, nothing new. This is true for all segmental, but illustrates how segmental can accommodate tight radii that often come. So speaking of tolerances, how much tolerance you have will be a function of this decision. Are you going to have plinths on your structure, or are you going to go plinthless? So they're shown in the picture on the left. Rail is sitting on fasteners, but those fasteners are attached to a plinth. And then on the right, again, rail and fasteners, but in this case, the fasteners are attached directly to the deck. So if you go plintless, precise casting tolerances are required. So there's going to be jigs like you see here in the picture. These things need to be located precisely when you're casting each segment. It's very coordination heavy. The precaster, geometry control folks, the track design team, all these people have to be on the same page to make sure this gets done right. Because the tolerances and the ability to adjust later is minimal. There are shims that can be done, but there's a limit to how much it can be shimmed. So it needs to get done right the first time. But if you can achieve it, then you don't have to deal with the weight of the plinths and the construction costs of the plinths. Excuse me. Plinths. So these give you a little more precasting and erection tolerances. So super elevation can be handled with plinths. You don't have to deal with that with your segments. Excuse me. And the separation of the rail from the top of the deck is beneficial for both system and drainage issues. So that's another advantage. You do have to put the starter bars in the segments in the precast yard. So there's no, we'll have to coordinate that and get that in the right spot in the precast yard. But much less tolerance than the embeds for the fasteners themselves. So speaking of embeds, as we mentioned in the design side, there's tons of stuff on the deck, and that stuff needs to generally be located in the precast segments and placed there. So some examples of that. So here we're showing a signal head. There's an anchor for that needs to get located and put in the segment so that it's in the right spot when those segments are erected. Another example here, and again, this is one of many, but again, meant to illustrate that there's a lot of stuff, and that stuff needs to be located in the segment. So here we're looking at kind of a secondary pour block that was cast against the exterior curve of the box girder to help support this CCTV pole. And there's, obviously form savers and sleeves in the precast segment that need to be located appropriately to get that spot. So again, one example of many to illustrate that there's a lot of coordination needed on the construction side as well. Okay, so now we got all our segments cast. What do we do with them? So the good news is we're going to erect them the same way we would erect a highway segmental bridge with a lot of the same equipment. So you can see a couple examples here using erection gantries. This is a common way for span by span construction, and like in highway bridges, linear construction is typical. With rail bridges, again, similar concepts to what's done for highways, but oftentimes with rail bridges, you might run into some of these things a little more often. And what are those things? Well, you might have some sharper radii to deal with, some curved alignments, because of different situations on the ground. You might have some variable substructure types to help accommodate, getting the guideway over certain things, and your erection equipment needs to accommodate all that. So again, nothing terribly different or new, but important. Here's showing again another animated video that just again illustrates how the construction equipment will need to accommodate the conditions in the field. So in this case, again, a tight radius. There's a temporary kind of pier bracket there you can see on the column on the right of the screen, and that's meant to help launch the girder. And then once the girder is launched, it can slide over and get supported like it normally would. And now you're effectively hanging segments the same way you'd be hanging segments for any type of segmental bridge. I'm seeing now that the video might not be, guys. So I'll pause here for a minute and see if it catches up. Okay. Yep. Not sure if anybody got to see that. The bar is on my screen, but if not, we'll move on.
Yeah, it showed fine.
Okay, good. Okay, next slide here. So urban settings. So again, rail bridges oftentimes are in urban settings, and so your equipment has to accommodate that. So here we're in downtown here in Chicago, and you can share the challenges of having to navigate that erection gantry in this kind of situation. But you can also appreciate why they decided to go with precast, because they can move a lot of those construction activities to a precast facility offsite, and that was the motivation for the desire to go segmental for this job. So again, similar equipment that you might see for any kind of segmental bridge, but in this case, because of all that deck furniture we talked about previously, your equipment has to obviously avoid that stuff. So here it's maybe a little tricky to see, but if you look at both the schematic and the picture, you can imagine those wheels for that segment transporter are going right over that line of plinth bars. So those plinth bars obviously can't be sticking out at the top of the deck. Those need to be either form savered or post installed. So again, example of something that just needs to be coordinated and planned accordingly. Yeah, all the previous slides we're talking about individual segments getting erected, but of course there are some full span erection schemes as well. So you can launch a full span like you see there on the picture on the left. And as we talked about with the narrow U, there's the ability to erect those full spans as well. In this case, picking with a couple of cranes. Last item here on construction stuff is rail installation. So typically it's done top down. The rails are all laid out, and if they're CWR, they're going to get all welded together. They can then be aligned and set, precisely to where they need to be. The plinth bar can get installed, anytime in there. And then we want to get the fastener inserts in the right spot. So typically that's done with templates that are temporarily attached to the rail, like you kind of see it in these pictures. and really it needs to be done precisely to get those inserts in the right locations. Then the formwork for the plinths can be installed, and the concrete can get placed. And this whole time the rail alignment and location and all that is being continuously monitored and tweaked. And then after the plinths are cast, then you can go back and install the permanent fasteners. Typically, they'll then be partially clipped in place, and then they won't get fully clipped until the rail is heated up to its neutral or stress-free temperature. Didn't really talk about this in the RSI analysis, but this is a temperature that the rail needs to be at when those rails are fully clipped. And it's an input into your analysis, so it needs to be consistent with what they're planning to do. Anyway, once those rails are fully clipped, then you move along. But once you get to like kind of the leading edge of your rail installation, you leave several hundred feet that's only partially clipped. And the reason for this is, we kind of hinted at it earlier, you don't want to terminate a fully clipped rail on an elevated structure, because it's going to impose a lot of forces due to temperature onto the structure. So you typically spread it out over hundreds of feet and partially clip it to kind of smooth that termination. But really the point here is the rail installation plan should be reviewed by the engineer, so to hopefully assess any impact it may have on the structure. Okay, and with that, then I'll touch into some maintenance issues. Not my background, but I'll do my best here to cover some of the important topics. Operation and maintenance manual is a good idea. So that should be part of the project deliverables. It gets everybody thinking about maintenance considerations during design and construction. Of course, inspections are a big part of the maintenance, and that needs to be done by qualified people on a routine basis. So no different for any other kind of structure. Rail bridges, though, have maybe a little more safety components associated with them. There's power systems up there that electrify the car and can kill you. So that needs to be addressed. And then, as we'll talk about here, it's a little harder to temporarily shut down rail lines when doing inspections, especially during revenue hours. So oftentimes these inspections are going to be taking place when the rail is in service. So it all needs to be planned accordingly, and safety measures need to be taken. So getting inspection access, what do you do? Well, you need to obviously get to all aspects of the structure. So from the top deck, typically that's going to be done through these emergency evacuation footwalks that you already have. Those can be used by the maintenance people to inspect and walk the track as well. As we mentioned, again, there's probably limited opportunity to reduce traffic, so there's a lot of traffic up there. Of course, if you have a box girder, you got to get inside that box girder. Bottom access hatches are preferable, largely just because top access hatches can oftentimes be in the train envelope, and you don't want to risk that. So, like all box girders, they need to be provided at regular intervals and provide access to every span, either through access hatch or through openings and diaphragms to get everywhere. I don't have details on this, of course, but whenever you go inside a confined space like this, there's requirements. OSHA has a bunch of them, and specific training and sometimes even specific equipment needs to be utilized if you go into one of these confined spaces. And then we need to look at the bottom and outside of the box too. So this is done conventionally, usually with man lifts or bucket trucks. Like I said, it's often better if possible to be done from ground brace equipment, so that you don't have to mess with the traffic overhead. So once we're checking out the bridge, what are we looking for? Well, same things that you'd look for on a highway bridge or any segmental bridge. So we're looking for cracking of the concrete, spalling, signs of moisture, signs of corrosion, delamination, anything like that. We're going to spend obviously a lot of attention on post-tensioning, any kinks, signs of moisture, can do some sounding as well, things like that. So all stuff that's typical for any maintenance manual. Again, like any other bridge too, there's expansion joints and bearings, and we want to take a look at those. So no different for a rail bridge, except as we mentioned that there may be a few more of these, more joints and more bearings to look at. And then, as we mentioned, there's going to be CWR crossing those joints, and those should be given close attention. Let's look at that CWR, look at the rail, any signs of distress or cracking or anything like that needs to be noted, of course. So yeah, brings me to inspecting the rails. Well, of course, you have to inspect them, inspect the fasteners, inspect the plinths. All these things need to be looked at. The rail alignment, like we talked about, it can change a little bit over time. It can wear down. It needs to be that and inspected and monitored. Power systems. So a whole slew of inspection items associated with them as well. Anybody that's going to be up there on the deck, whether they're inspecting the power systems or not, needs to be well aware of the safety considerations. So you generally always assume that third rail or that overhead canary system is energized, unless you know it to be powered down and locked out. Typically, you're going to be using non-conductive equipment to help safeguard that, and you're going to be looking at everything from the system itself to any support components. Other systems. So a bit of a catch-all here, but like I mentioned, there's going to be tons of cable trays, tons of hangers, conduits, cables, all sorts of things running along the bridge and supported from the guideway. And these things all need to be looked at. Pay particular attention to where those things transition, either from the structure, the superstructure to the substructure, or where they cross expansion joints, because in those cases there's going to be differential movement, and you want to make sure that those systems can allow for that. I talked a little bit about straight current previously. Here, it's just important that the inspectors also know what this system is, and that every part of the system needs to be in place for it to function properly. Copper cables are a theft target, so you know, made aware that you know, all this stuff needs to be in place. Last topic here is bridge cleanliness. So again, applies for all bridges, but can be a little more important for rail structures. Debris and sand tend to accumulate a little faster on rail bridges than roadway bridges, and that debris can accelerate degradation of the deck. And then, as you can see here in the schematic, a lot of the equipment that's mounted to the deck needs to be isolated, you know, with pads or bushings or washers or bushings. And so if there's debris accumulation, that can negate the isolation. So you don't want that. And so that heightens the need to keep that bridge deck clean. So with that, hopefully some of these topics will help you, you know, identify some things that are unique about rail bridges and help you on your next concrete segmental rail bridge project. So with that, thank you all for your time, and I'll stick around for some questions.
Well, thank you. Thank you, David. That's great. I'll just hop in real quick here and introduce our Q&A moderator. We do have a few minutes for Q&A and a lot of really great questions that I've seen coming in. So our moderator for the Q&A is Mr. Tim Berry. He's a vice president and area manager for RS&H and their construction management practice. He has more than 20 years of industry experience, including construction management of 5 segmental bridge projects in Florida and Virginia. He's been an active member of ASBI for more than 15 years and is currently the chair of our ASBI grouting committee and is the past chair of the ASBI construction management practice group. So he's a professional engineer, and he earned a civil engineering degree from Michigan Tech University. So with that, I will turn it over to Tim to go through the questions with David.
Thank you, Greg, and David as well. Yeah, like Greg mentioned, a lot of great questions generated, which we love to see. So we'll just jump right into it, David. First one, someone wondering what software you use to do the rail analysis for these structures.
So our company here, we're pretty partial to Larsa 4D. We've been using that a while and are real comfortable with that. You know, there are a few other programs out there, but that's the one that we use.
Okay, thank you. As I go through these questions, I'm going to warn you, David. This topic is definitely beyond my expertise as far as. So I'll just read the questions, and hopefully you'll be able to understand them much better than I. So next question: is there any damping conservation in the details of your analysis?
I'm sorry. Can you repeat that again?
Damping conservation.
So not sure the context here. Maybe we're talking about the vehicle structure interaction analysis. You know, there's damping in the suspension system of the vehicle. I'm not sure if that's what they're referring to.
Okay.
That can be considered in the rolling stock analysis. There are some studies out there that kind of show that it's conservative to ignore that. But yeah, there is software that can accommodate that and include that in your analysis.
Okay. I had a question regarding precast versus cast in place, and someone wondering, is there something that drives more towards precast versus cast in place option for the design?
Yeah, that's a good question. So, you know, with rail bridges, they're often long. There's a lot of typically long lengths of guideway that you're trying to build and construct. So that kind of lends itself to precast. You know, there needs to be a minimum kind of amount of length, a minimum number of segments to justify kind of the investment in the equipment and the precasting. So that tends to skew it towards precast. But there are certain situations where, you know, cast in place makes sense, and obviously it can be done and utilized just as well.
Okay. Interesting question. Someone referring to Eurocode, which has guidelines on vibration analysis and passenger comfort, and the frequency limit decreases. Is there a similar practice that you're aware of?
Yeah, I'm personally not too familiar with the Eurocode. I think it's pretty similar to what's in California high-speed rail criteria. Right. So, I mean, you know, again, the objective is to obviously maintain passenger comfort, and that's typically done by limiting the accelerations of the bridge. It's also affected by the suspension of the vehicle, but that's typically a separate topic. And so for us as the bridge folks, we try to limit the acceleration of the bridge. And I'm not sure if I'm answering the question here, but I think criteria that we use in the US is likely similar to what's in the Eurocode, but I can't really speak too much to what's in the Eurocode.
Sure. Okay. Another question, narrow U versus box. Can you explain the risk for accommodating derailment load?
The risk for accommodating. Well, so with the U, like we said, you know, the lateral derailment there can be restrained by the vertical portion of the U. So, you know, it needs to be designed for, and that wall needs to be accommodated or needs to be designed accordingly. With the box girder, you'll typically have a separate thing. It'll usually be either part of the plinth or adjacent to the plinth, you know, kind of a curve that'll act as that purpose. So, you know, you can provide the same level of protection. It's just an extra item in the case of a box girder.
Okay, thank you. Question regarding inclusion of rolling stock. When does the inclusion of the rolling stock become critical, or conversely, when is it appropriate to exclude?
Yeah, good question here too. So, you know, I would say this probably varies criteria to criteria. I want to say sometimes if you meet some of those deflection limits and you meet that, you know, first mode of vertical vibration, you know, Hertz limit, then you might not have to do a rolling stock analysis at all. You know, from my experience, it tends to not be too much of an issue for light rail transit, you know, mostly because the speed of the vehicles are such that you're pretty far away. The loading frequency of, let's say, the vehicle going on the span and coming off the span is typically far away from what the natural frequency of that span is. It becomes more of an issue with high-speed rail. So I would think it would be hard to not go through an analysis if you're working on a high-speed rail project. And yeah, that's kind of where I would lean.
Okay, I know you had in the presentation you mentioned seismic seismic considerations. We had a question regarding what do you think, if you have any experience or any opinion on lead rubber bearings and bridges that allow movement under certain limit?
Yeah, good question there too. I don't have much experience with lead rubber bearings, but typically with segmental, we're fans of using elastomerics, and those I think can be interchangeable to a lot of ways. I mean, I think of well, the more I speak, the more it'll be apparent I don't know enough about it, so I probably can't answer that one.
Okay, we're at the top of the hour. Like Greg mentioned, if people need to drop off, we understand, but we're going to try to run through a few more of these. Some late breaking questions coming in here too.
Okay.
Question regarding, do you include the vehicle model and the FEA model when running rolling stock analysis?
Yeah, so tried to address this before. So I think ideally you could. Again, there's a suspension. The suspension of the vehicle can be included in that VSI analysis. Again, I'm aware of a few studies that have kind of shown that it can be ignored, and the results are generally conservative because the dampening and the suspension of the vehicle helps the dynamic performance. So if you can get away with ignoring it, it's going to be easier. But if your software can accommodate it, and if you know that information, then you can include it.
Okay. Is there some design rules how to place the shear keys between the segments and the top and bottom slabs?
Shear keys. So I assume this is like the shear keys
for the precast segments, I would assume.
Yeah, the match cast joints.
Yeah.
Yeah, so it's kind of industry practice. I can't recall, there may be some guidelines in AASHTO about it, but effectively the keys in the web are there to help transfer shear, and the keys in the top and bottom slabs are to help align the top and bottom slabs. So because the top and bottom slab keys are kind of for alignment, it's a little harder to pinpoint exactly how many and how big, but we tend to kind of go with what's worked in the past.
Okay. Question about grounding of the segments. How is that done, or is there what is usually done there?
Yeah, so this is getting to the point where I might be talking more than what I'm capable of answering, but from what I understand, again, the idea is you're going to bond rebar together, collect, that bonding for precast obviously needs to get from segment to segment, and then across span from span to span, and then that can all be grounded or effectively collected and then taken to the ground, and maybe there's a rod in the ground or an anode in the ground, something like that you ground to. That's my general understanding of it, but not my area of expertise.
Understood. Okay. Couple more here before we probably should wrap it up. Question about some owners want ballasted track. How does this affect the design if it's something the owner would like? And how do you account for this?
Yeah, that's a good question. Personally, haven't worked on a ballasted track project, but it changes things. So the ballast is pretty heavy, so that's one thing. You got to accommodate the weight of the ballast. But it does simplify that RSI analysis quite a bit, because now the rails are really independent of the structure beneath, at least as far as I understand it. The ballast basically allows them to slip and move past each other without really interacting. So I think it simplifies that aspect, but you've got to handle the weight of it, and then I think from a maintenance standpoint too, I think it tends to be a little trickier to maintain, because, well, it's hiding a lot of the deck, so you can't really see what's happening underneath there. And then I think just ballasted track in general is a little harder to maintain from what I understand.
Okay. Greg, I think we'll go ahead and do one more here, and then we'll wrap it up. What is a typical bearing type and bearing arrangement for simply supported railway spans?
Yeah, so, you know, like elastomerics are, you know, neoprene bearings are typical. I didn't really talk much about this, but, you know, they kind of have like a floating span concept that is good, attractive, easy to build, but you got to restrain movements of it too. You don't want the bearings walking, you don't want the spans walking. So typically that's handled with shear keys that are at the center of the pier and you know, effectively restrain the pier segments in both transverse and longitudinal direction. So those can be gapped. There can also be like softening or whatever between the interface of the shear key and the pier segments. But that's a common system that's used.
Okay. Well, David, appreciate your time and handling some of these questions after the fact. It's been great, generated a ton of interest. So obviously it was a great presentation. We appreciate it. So Greg, I will turn it back to you.
All right, thank you, Tim. Yeah, David, I'll just echo a great presentation. Appreciate your time today. I just put up in the chat for everybody a link to the guide document that ASBI published earlier this year. There's a link there in the chat. You can click it and get to it, or alternatively, you can always go to the ASBI website, and under the publications tab, you'll find it in the list of the publications that we have available. If you can't find the ASBI website, there's a little QR code there for you on screen as well. If you want to hit that, you'll be taken directly to the ASBI website. So with that, we will wrap up the webinar. I know we weren't able to get to everybody's questions. Appreciate those, though, folks submitting questions. There were a couple questions about camber in the design and deflections. And I would say it was kind of outside the scope of this particular presentation. I'll use this as a teaser for tune in next month, because we're going to be talking a lot more detail about segmental construction, and certainly be talking about some of the geometry control that goes on in the construction to ensure that elevations come out to be where they're supposed to be. So with that, we will wrap up. Again, thank you, David. Appreciate your time today. Outstanding presentation. So thank you, everybody. We'll sign off.
You bet. Thanks. Bye.